Hello everyone. This is the first lesson in grade 9 math. Today we are doing number sets, and I promise by the end of this lesson you will look at numbers in a whole new way. So here's what we will cover today. Why did humans need to invent zero? How do number sets fit inside each other? What makes a number irrational? We'll look at the perfect squares, we'll look at the sizes of an infinity, and we'll look at what density is, and at the end we'll look at a real world example. So let's begin. Okay, let's see where zero came from. Why did humans invented zero? So look at this timeline. Around 300, it's not 3000, but 300 BCE. So BCE is basically before Common Era, CE is Common Era. So that's how we refer to ages in math. But normally we call it before Christ and AD. So around 300 BCE, the Babylonians had a problem. They were writing numbers on clay tablets. But how do you write nothing in a number? They made a simple placeholder symbol, nothing exactly our zero, but the idea was born. Then around 628 CE, a mathematician named Brahmagupta did something big. He wrote rules for zero. 5 plus 0 equals 5, 5 times 0 equals 0. He also tried dividing by 0, which we still argue about today. A couple of hundred years later, the Arabic world spread these ideas. Al-Khwarizmi helped bring Hindu-Arabic numbers including 0 to more people. And by 1202, a man called Fibonacci wrote a book. This book brought 0 into European trades and business. Merchants loved it. It made counting money much easier. Now, why does this matter? Without 0, you cannot write 10, you cannot write 100, you cannot write 1000. Place value, the way all our numbers work, needs 0. No 0 means no algebra means no computer, and no computer means no internet. One small symbol invented by real people in real cultures over thousands of years, and it changed everything. Okay, now let's look at the number families. Not just the definition, but with some real life examples. Okay, here the first one, suppose you are counting apples, right? 1, 2, 3. So you need the numbers to count apples. So these forms the natural numbers. So the natural numbers are the ones with positive numbers which help you to count. Now suppose all your apples are taken, the basket is empty, right? So in this case you need 0 to represent that. So the number 0 falls under another family called the whole numbers. So the whole numbers contains 0 as well as the positive numbers. We'll see this in detail in the next slide, where I'll be showing you one family of numbers sits inside the other family. Now suppose you owe 50 rupees to somebody. So this can be denoted by minus 50. So the negative numbers. So you need negative numbers. So the family, when you add negative numbers to the above family, you get integers. Now suppose you want half pizza. So now there's a need to represent fractions. So the fractions and decimals falls under the family called rational numbers. There are some numbers which cannot be written as fractions or decimals. Those are called irrational numbers, like the diagonal of a square. So suppose you have a square of size 1 and the diagonal of this will be of size root 2. So root 2 cannot be expressed in terms of fractions. So it's an irrational number. Another example is pi. The value of pi is 3.1415 and so on. So that cannot be represented as either a fraction, it belongs to real numbers. Let's bring up this picture here. So now this is another way of representation of the number families. Here you will see that the smaller box sits inside a bigger box, and that box sits inside another bigger box. So this is another way of representing the number families. Here the smallest box is the natural numbers. So all the positive numbers, we call them natural numbers. If you add 0 to the natural numbers, what you get is whole numbers. So the whole numbers contains 0 as well as the positive numbers. Now when you add negative numbers to the whole numbers, you get integers. So the integers contains the negative numbers, the number 0 and the positive numbers. Now, when you add fractions or decimals to integers, what you get is the rational numbers. So the rational numbers contains integers, the negative numbers, the number 0 and the positive numbers. And then when you add irrational numbers to rational numbers, what you get is the real numbers. So real numbers is the biggest family which contains all the other numbers. So for example, if suppose the number 0, so the number 0 is a whole number, it is also an integer because it sits inside that box, it is also a rational number, and it is also a real number. So if you say -1, so this is an integer, it is not a whole number and it is not a natural number, but -1 is a rational number, it is also a real number. I hope you got the idea. So now let's look at some special subsets of numbers. Let's first look at the even and odd numbers. So you know an even number is one which is divisible by 2 and there is no remainder, whereas whenever you divide a number by 2 and you get a remainder, that's an odd number, right? And then on the screen you can see the numbers in blue are all even numbers because when you divide them by 2 you do not get any remainder, whereas the numbers in pink, when you divide them by 2 you will always get a remainder of 1. Okay, so next are the prime numbers. So the prime numbers are those which are divisible by themselves or by 1. And the fun fact, only number 2 is an even prime number, whereas if you see all other prime numbers are always odd numbers. Okay, let's now look at what is a perfect square. Now you know what is a square, right? When you multiply the number to itself, the number which you get is called a square. For example, here 4 is the square of 2 because when you multiply 2 into 2, you get 4. When you multiply 3 by 3, you get 9. When you multiply 4 by 4, you get 16. So here 16 is a square, 9 is a square, and so on. Now, what the perfect square means. Now, if you look at the pictures here, so here when you place, for example, 4 tiles, they perfectly fit in a square. And that's why it is called a perfect square. Here, if you place 9 tiles, and they fit perfectly in this square. So it's called a perfect square. The square of a whole number is always a perfect square. Now, the next question which can come to your mind is, what is a non-perfect square, right? So let's look at an example. If you multiply 1.5 into itself, what you get is 2.25, right? Now, is this 2.25 a perfect square? No, right? Because if you say, for example, place 2.25, so say this becomes 2.25. So if you see the shape which you will get here is something like this, right? So this is not the shape of a perfect square, and hence 2.25 is not a perfect square. The other fact which is concealed here is that to get the next perfect square, you always add the next odd number to it. So for example, to get the next square number from 1 to 4, you add the odd number 3. The next odd number is 5. So if you add 5 to 4, you will get 9. If you add the next odd number 7 to 9, you will get the next perfect square, which is 16. Also, this is visible from the pictures here. So for example, if you add 3 more tiles, you get 4. Here you add 5 more tiles, and here you add 7 more tiles to get the next perfect square. I hope this is clear. All right, let's talk about rational and irrational number now. So what is an rational number? A rational number is a number which can be written as a fraction. For example, here you can write 5 as 5 by 1, 0.75 as 3 by 4, 0.33 as 1 by 3. Also, you notice here that in case of rational number, either the decimal stops or the decimal keeps on repeating here. So because here 1 by 3, if you change it into decimal, the 3 will keep on repeating. Now, what is an irrational number? A irrational number is one which cannot be written as a fraction. For example, if you see here, the value of square root of 2. So here, this is the value and this will keep on going. It will never stop. For example, the value of pi. If you see here, it's 3.1415 and it will keep on going. It never stops. So now you can define rational and irrational number. A rational number is one which can be written as a fraction, and in this case the decimal stops or keeps on repeating. Whereas in case of irrational number, it cannot be defined as a fraction, and in this case the decimal is non-terminating and non-repeating. Let's look at a real example here. If you draw a square of size 1 and join one corner to the other, what you get is the diagonal, and the size of this diagonal is square root of 2, which is a irrational number, and this cannot be defined as a fraction. Okay, let's talk about density now. So density, what is a density? So we'll look at the definition a bit later, but let's see with an example first. So here, if you see, there's a number line where you have numbers from 0 to 20. So in total, there are 21 whole numbers. Now, if I ask you how many perfect squares can you find within this range and how many odd numbers you can find within this range. So here, if you'll see, there are in total 5 perfect squares within this range, whereas there are 10 total odd numbers within this range. So now let's come to the definition here. So density is defined as count of a particular type by the total count or the total range. So here, if you see how many perfect squares are there, 5 out of total 21 numbers. So the value comes to 0.24. And here you have 10 odd numbers out of total 21. So the range, so the value is 0.48. So in this case, the odd numbers are more denser than the perfect square in a given range. Let's look at density with some more examples. So here, the same thing between 0 to 20, we have already seen this. Let's see what is next. Now let us look at this example. If somebody asks you, are the integers more denser than real numbers? The answer is no. The real numbers are more denser. Now, what does that mean? Let's look at an example here from -2 to 6. So in total, there are 7, 8, 9 numbers, right? Now, between these, how many integers are there? So you'll see there are 9 integers. But now if we talk about real numbers, how many real numbers can be on this number line? Now, you know what is a real number by definition, right? So a real number includes rationals, irrationals, the integers, and everything, right? So let's take, for example, here, if I write, say, this is 0.5, right? And let's say here's another number, 0.75, right? So in this way, you can write infinite number of real numbers in this number line. So the real numbers are infinitely denser than the integers because there are only a finite number of integers within this range, whereas there will be infinite number of real numbers. So we can say the real numbers are infinitely more dense than the integers. Okay, now let's see the term limit and infinity. So here you can see some growing patterns and some shrinking patterns. So let's go through this. So here you can see this pattern, which is the multiple of 2's. This is growing, and to whatever number you can think of, there will be always a multiple of that number. So we say that this pattern grows infinitely and its limit is positive infinite. So we can write it like this, positive infinite. So the next pattern which you can see here is a perfect square pattern. And so whatever perfect square you can think of, you will always get a next perfect square. So this pattern also grows infinitely, and we say its limit is positive infinite. All right. So now let's move to the shrinking pattern here. So here you can see this as a shrinking pattern where the next number is the half of the first one. Similarly, this number is the half of the first one. So this is shrinking and the value is getting closer and closer to 0, but it never reaches 0. So here we say that the limit of this pattern is 0. So this idea where a pattern getting close to a fixed value forever is called a limit. So here in this case, the limit of this pattern is positive infinity. Here the limit of this pattern is 0. There can be other patterns as well where the limit can be the other numbers. Say for example, if you consider 0.9, then you can write the next number is 0.99, and then you can write the next pattern as 0.999. So in this case, the value is approaching 1, but it is never 1. So in this case, we say the limit of this pattern is number 1. I hope you got the idea. Okay, now for the real world part. Here is my question. Can one triangle hold an infinite number of triangles inside it? The answer is yes, and I'll show you exactly how. This is called the Sierpiński Triangle. It is a fractal, a shape made by repeating one simple rule again and again. So we start with one solid triangle, okay, and let's call it step 1. Now we take this triangle and cut it into 4 smaller triangles, and we remove the middle one. Now we are left with 3 triangles. So if you see here, the number of the triangles has increased, but the area of the triangle has decreased. So earlier we had one big triangle and the area was the full area of the triangle. Now since we have removed one part from it, we are left with 3 triangles, and the area of these triangles have also now decreased. Now let's repeat the same process again and cut it into more equal parts, and now we are left with 9 triangles, and now the area of each triangle is even smaller. If we repeat the process with 27 triangles, and if you notice, the area of the triangle is even smaller. So as we repeat the process, the number of triangles is increasing while the area is decreasing. So as we keep on repeating the steps, the number of triangles will keep on increasing while the area keeps shrinking. So in this one picture, we see all 3 big ideas from today. Infinity, the number of triangles, grows without end, and a limit, the area, shrinks towards 0 but never quite reaches it. And the density, at every step, more and more details appears inside the same space. Fractals like this appear in nature too. You might have seen snowflakes, the coastlines, all follow the same idea of simple rules repeated forever. Okay, now let's look at some common mistakes students usually do. So the first one is -3 a natural number. So -3 is not a natural number because natural numbers are positive, right? So -3 is an integer. Is 0 a natural number? 0 is not a natural number because it's a whole number, right? The natural numbers are only the positive numbers. So is 0.33 a rational number? So many students mistake this and they say it's a rational number, but it is not. It's a rational number because here the decimal part is repeating, and so it's a rational number. Now is root of 4 is irrational? No, root of 4 can be written as 2, which is a natural number. So root 4 is not a rational number. Is infinity a number? So as we have already seen infinity and the concept of limit, so infinity is not a big number, it's just a concept, right? It doesn't have a actual value. I hope these examples will help you to think deeper into this topic. So now let's put it all together. The number families fit inside each other. Natural numbers, inside whole numbers, inside integers, inside rationals, inside real. Rational numbers are fractions or decimals that stop or repeat. Irrational numbers never end and never repeat. We have special subsets too: even numbers, odd numbers, primes, and perfect square. Density tells us how crowded a set is. It is the type divided by the total. It is a probability. Infinity means a pattern never stops. There is no biggest number. And a limit is a value the number gets closer and closer to, but never quite reach, like getting closer to zero.